Hello, can everyone hear me? Hello, can everyone hear me? Mm, Uh, Let me change to full screen. Okay, so last stream I learned about threads. This stream I'm going to be studying locks and maybe this chapter as well. Okay, let's see. 22 pages. I think I will only read this chapter this stream. Single page is fine. From the introduction to concurrency, we saw one of the fundamental problems in concurrent programming. We would like to execute a series of instructions atomically. But due to the presence of interrupts on a single processor, we couldn't. In this chapter, we thus attack this problem directly with the introduction of something referred to as a lock. Programmers annotate source code with locks, putting them around critical sections and thus ensuring that any critical section executes as if it were a single atomic instruction. As an example, assume our critical section looks like this: the canonical update of a shared variable. Of course, other critical sections are possible, but such as adding an element to a linked list or more complex updates to shared structures. But we will just keep to this simple example for now. So critical section is where the resources are shared, right? So multiple threads are using this balance variable. To use a lock, we add some code around the critical section like this. So lock mutex. What is mutex? Why do we call it that? And then lock the address of mutex and then unlock. A lock is just a variable, and thus to use one, you must declare a lock variable of some kind, such as mutex above. This lock variable, or just lock for short, holds the state of the lock at any instant in time. It is either uh, available. It is either available or unlocked or free, and thus no thread holds the lock, or acquired, and thus exactly one thread holds the lock, and presumably in a critical section. We could store other information in the data type as well, such as which thread holds the lock or a queue for ordering lock acquisition. But information like that is hidden from the user of the lock. The semantics of lock and unlock routines are simple. Calling the routine lock tries to acquire the lock. If no other thread holds the lock, it is free. The thread will acquire the lock and enter the critical section. This thread is sometimes said to be the owner of the lock. If another thread then calls lock on that same lock variable, it will not return while the lock is held by another thread. In this way, other threads are prevented from entering the critical section while the first thread that holds the lock is in there. So wait, let's say another thread reaches the exact same code. Like these lines of code are in two threads. Another thread reaches this exact same line of code. So when it reaches lock mutex, does it just pause until mutex is available? Is that what happens? Once the owner of the lock calls unlock, the lock is now available again if no other thread are waiting for the lock. The state of the lock is simply changed to free. If there are waiting threads stuck in lock, one of them will eventually notice or be informed of this change of the lock state, acquire the lock, and enter the critical section. So in CPU, with the in the context switch that happens in the CPU, the time sharing thingy, the CPU switches between processes and even threads, right? So when a thread is waiting for a lock, does it switch over there too? Or does it only go there when the lock is free? Locks provide some minimal amount of control over scheduling to programmers. In general, we view threads as entities created by the programmer but scheduled by the OS in any fashion that the OS chooses. Your locks yield some of that control back to the programmer. By putting a lock around a section of the code, the programmer can guarantee that no more than a single thread can ever be active within that code. Thus, locks help transform the chaos that is traditional OS scheduling into a more controlled activity. The name of the POSIX library uses the name that the POSIX library uses for the lock is a mutex, as it is used to provide mutual exclusion between threads. If one thread is in the critical section, it excludes the others from entering until it has completed the section. Thus, when you see the following POSIX threads code, you should understand it is doing the same thing as above. So P threads, mutual exclusion, type, and lock. And then we have some initializer. So what do we put over here? So we have this address of lock. Balance is updated. Now we unlock. You might also notice that the POSIX version passes a variable to lock and unlock, as we may be using different locks to protect different variables. So is this lock variable, is this a global variable? Doing so can increase concurrency instead of one big lock that is used anytime critical section is accessed. One will often protect different data and data structures with different locks, thus allowing more threads to be in locked code at once, a more fine-grained approach. By now, you should have some understanding of how lock works from the perspective of a programmer, but how should we build a lock? What hardware support is needed? To build a working lock, we will need some help from our old friend, the hardware, as well as our good pal, the OS. Over the years, a number of different hardware primitives have been added to the instruction set of various computer architectures. While we won't study how these instructions are implemented, we would study how to use them in order to build a mutual exclusion primitive like a lock. We will also study how the OS gets involved to complete the picture and enable us to build a sophisticated locking library. Before building any locks, we should first understand what our goals are and thus ask how to evaluate the efficacy of a particular lock implementation. To evaluate whether a lock works, we should establish some basic criteria. First is whether the lock does its basic task, which is to provide mutual exclusion. Basically, does the lock work? preventing multiple threads from entering a critical state. The second is fairness. Does each thread contending for the lock get a fair shot at acquiring it once it is free? Another way to look at this is by examining the most extreme case. Does any thread contending for the lock starve while doing so, thus never obtaining it? The final criterion is performance, specifically time overheads added by using a lock. There are many different cases that are worth considering here. One is the case of no contention, when a single thread is running and grabs and releases the lock. What is the overhead doing so? Another is the case where multiple threads are contending for the lock on a single CPU. Okay. So, one of the earliest solutions used to provide mutual exclusion was to disable interrupts for critical sections. This solution was embedded for a single processor system. Code will look like this. Okay. So, lock disable interrupts and unlock enable interrupts. Assume we are running on such a single processor system. By turning off interrupts using some kind of special hardware instruction before entering a critical section, we ensure that the code inside the critical section will not be interrupted and thus will execute as if it were atomic. When we are finished, we re-enable interrupts and thus the program proceeds as usual. The main positive of this approach is its simplicity. You certainly don't have to scratch your head too hard to figure out why this works. The negatives, unfortunately, are many. First, this approach requires us to allow any calling thread to perform a privileged operation and thus trust that this facility is not abused. As you already know, anytime we are required to trust an arbitrary program, we are probably in trouble. Here, the trouble manifests in numerous ways. A greedy program could call lock at the beginning of its execution and thus monopolize the processor. Worse, an errant or malicious program could call lock and go into an endless loop. In this latter case, the OS never regains control of the system. I mean, what if we disable interrupts, but we allow the OS to take control once in a while and then go back to the same thread? Like, only have time scheduling between the OS and that one thread. And if the OS detects something fishy, the OS can like delete that thread. Second, the approach does not work on multiprocessors. If multiple threads are running on different CPUs and each try to enter the same critical section, it does not matter whether interrupts are disabled. Threads will be able to run on other processors and thus could enter the critical section. As multiprocessors are now commonplace, our general solution will have to do better than this. Third, turning off interrupts for extended periods of time can lead to interrupts becoming lost, which can lead to serious system problems. Imagine, for example, if the CPU missed the fact that this device has finished a read request. How will the OS know to wake the process? How will the OS know to wake the process waiting for a said read? For these reasons, turning off interrupts is only used in limited contexts as a mutual exclusive primitive. For example, in some cases, an operating system itself will use interrupt masking to guarantee atomicity when accessing its own data structure, or at least to prevent certain messy interrupt handling situations from arising. This usage makes sense as the trust issue disappears inside the OS. To move beyond interrupt based techniques, we will have to rely on CPU hardware and the instruction it provides us to build a proper lock. Let's first try to build a simple lock by using a single flag variable. In this failed attempt, we will see some of the basic ideas needed to build a lock and see why just using a single variable and accessing it via normal loads and stores is insufficient. In this first attempt, the idea is quite simple. Use a simple variable to indicate whether some thread has a possession of a lock. So structure int flag lock. So init lock mutex. So mutex flag 0. Okay, so when we initiate it, we set the flag to 0. And when we lock it, we set the flag to 1. Wouldn't this waste CPU cycles? This while loop, void unlock, turn the flag to 0. Um, the first thread that enters the critical section will call lock, which tests whether the flag is equal to 0 and then sets the flag to 1 to indicate that the thread now holds the lock. When finished with the critical section, the thread calls unlock and clears the flag, thus indicating that the lock is no longer held. If another thread happens to call lock while the first thread is in critical section, it will simply spin wait in the while loop for that thread to call unlock and clear the flag. Once the first thread does so, the waiting thread will fall out of the while loop, set the flag to 1 for itself, and then proceed into the critical section. Unfortunately, the code has two problems. One of correctness and another of performance. The correctness problem is simple to see once you get used to thinking about concurrent programming. Imagine the code interleaving in figure 28.2, assuming flag 0 to begin. So call lock while flag 1 interrupt switch to thread 2. Call lock. So in thread 2 it calls lock while flag 1 turn the flag to 1. Oh, this. So thread 1 reads this and finds out that this is false. So it goes into the critical section, right? Yeah, this is false. So now it sets the flag to 1. And thread 2, while flag 1. Uh, so this is false, but then it switches to thread 2. This is true, and then it sets the flag to 1. And then goes back to thread 1, and thread 1 also sets the flag to 1. So none of them are stuck in a while loop. As you can see from this interleaving with timely interrupts, we can easily produce a case where both threads set the flag to 1 and both threads are thus able to enter critical section. This behavior is what professionals call bad. We have obviously failed to provide the most basic requirement, providing mutual exclusion. Performance problem, which we'll address more later on, is the fact that the way a thread waits to acquire a lock is already held. That is already held. It endlessly checks the value of a flag, a technique known as spin waiting. Spin waiting wastes time waiting for another thread to release the lock. The waste is exceptionally high on a uni processor, where the thread that the waiter is waiting for cannot even run. Thus, as we move forward and develop more sophisticated solutions, we should also consider ways to avoid this kind of waste. Building working spin locks with test and set. Because disabling interrupts does not work on multiple processors, and because simple approaches using load and stores don't work, designers started to invent hardware support for locking. The earliest multiple multiprocessor systems, such as Burroughs P5000 in early 1960s, had such support. Today, all systems provide this type of support, even for single CPU systems. The simplest bit of hardware support to understand is known as a test and set or atomic exchange instruction. We will define what the test and set instruction does by the following CPU code snippet. So test and set, old pointer, new pointer, then return the old pointer. What is this used for? Fetch the old value, store new into old pointer, return the old value. Why even do this in a separate function? You already have the old value in the parent function, right? What the test and set instruction does is as follows. It returns the old value pointed by the old pointer and simultaneously updates the set value to new. The key, of course, is that this sequence of operations is performed atomically. The reason that it is called the test and set is that it enables you to test the old value while simultaneously setting the memory location to a new value. As it turns out, the slightly more powerful instruction is enough to build a simple spin lock. As we now examine in figure 28.3, or better yet, figure it out yourself. So struct lock flag. So initiate, set the flag to 0. So void lock test and set. So lock flag, set it to 1 and check if it's equal to 1. And unlock is the same. So how does this improve the thing? Suppose both the threads reach this part, they will both set the flag to 1, right? Suppose in thread 1, the CPU reaches here, sets the value of the old pointer to 1, and then goes to thread 2. Thread 2 then comes here, sets the value to 1. No, wait, it won't. Hold on. With thread 2, when it checks the logs flag, it would be equal to 1, not 0. Yeah, it sets the value to 1, and then the previous value would be 1, right? But in thread 1, the old value is 0. Okay, how about this? What if in thread 1, it reaches over here? So old is 0, and new over here is 1. And in thread 2, it reaches over here, so it sets this to 1. And the old value is still 0 because old pointer was not set in thread 1. So in thread 2, it returns 0. In thread 1, it also returns 0. Yeah, isn't that an issue? Let's make sure we understand why this lock works. Imagine first the case where a thread calls a lock and no other thread currently holds the lock. Thus, flag should be 0. When the thread calls test and set flag 1, the routine will return the old value of flag, which is 0. Thus, calling thread, which is testing the value of flag, will not get caught spinning in a while loop and will acquire the lock. The thread will also atomically set the value to 1. What do you mean atomically? So this entire thing happens in one go. Like, so the context switch won't happen. The interrupt won't happen over here. Thus indicating that the lock is now held. When the thread is finished with its critical section, it calls unlock to set the flag back to 0. The second case we can imagine arises when one thread already has the lock held. Flag is 1. In this case, this thread will call lock and then call test and set as well. This time test and set will return the old value at flag, which is 1, while simultaneously setting it to 1 again. As long as the lock is held by another thread, test and set will repeatedly return 1, and thus this thread will spin and spin until the lock is finally released. When the flag is finally set to 0 by some other thread, the thread will call test and set again, which will now return 0 while atomically setting the value to 1, thus acquiring the lock and enter the critical section. By making both the test of the old lock value and set of the new value a single atomic operation, we ensure that only one thread acquires the lock. And that's how to build a working mutual exclusive primitive. You may also understand why this type of lock is usually preferred to as a spin lock. It is usually simplest type of lock to build and simply spins using CPU cycles until the lock becomes available. To work correctly on a single processor, it requires a preemptive scheduler. Without preemption, spin locks don't make much sense on a single CPU as the threads spinning on a CPU will never relinquish. From this example, you might get a sense of the approach you need to take to understand concurrent execution. What you should try to do is to pretend you are a malicious scheduler, one that interrupts threads at the most inappropriate of times in order to foil their feeble attempts at building synchronization primitives. What I mean scheduler you are. Although the exact sequence of interrupts may be improbable, it is possible, and that is all we need to demonstrate that a particular approach does not work. In the 1960s, I still don't know how to pronounce his name, posed a concurrency problem to his friends, and one of them, a mathematician named Theodorus Joseph Decker, came up with a solution. Unlike the solutions we discussed here, which use special hardware instructions and even OS support, Decker's algorithm just uses loads and stores, assuming they're atomic with respect to each other. Decker's algorithm was later refined by Peterson. Once again, just load and stores are used. The idea is to ensure that two threads never enter a critical section at the same time. Here is Peterson's algorithm. To see if you can understand the code, what are the flag and turn variables used for? So flag 0 and 1 is 0, turn 0, void lock. Self is the thread ID of the caller. Flag self is 1. Make it other threads turn. Turn is 1 minus self. while flag 1 minus self is 1 and turn is 1 minus self. Spin wait while it's not your turn. For some reason, developing locks that work without special hardware support became all the rage for a while, giving theory types a lot of problems to work on. Of course, this line of work became quite useless when people realized it is much easier to assume little hardware support. Further, algorithms like the ones above don't work on modern hardware, thus making them even less useful. Given a basic spin lock, we can now evaluate how effective it is along our previously described axis. The most important aspect of a lock is correctness. Does it provide mutual? Wait, hold on. Yeah. Does it provide next? Wait. Does it provide mutual access? The answer is yes. The spin lock only allows a single thread to enter the critical section at a time. The next axis is fairness. How fair is simple lock to a waiting thread? Can you guarantee that a waiting thread will ever enter the critical section? The answer here, unfortunately, is bad news. Spin locks don't provide any fairness guarantees. The final axis performance. What are the cost of using a spin lock? To analyze this more carefully, we suggest thinking about a few different cases. In this first, imagine threads competing for the lock on a single processor. In the second, consider threads spread out across many CPUs. For spin locks in the CPU case, performance overheads can be quite painful. Imagine the case where the thread holding the lock is preempted within a critical section. Scheduler might then run every other thread, each of which tries to acquire the lock. Uh, each of which tries to acquire the lock. Okay. In the first, imagine threads competing for the lock on a single processor. In the second, consider threads spread out across many CPUs. For spin locks in the single CPU case, performance overheads can be quite painful. Imagine the case where the thread holding the lock is preempted within a critical section. The scheduler might then run every other thread, each of which tries to acquire the lock. In this case, each of those threads will spin for the duration of the time slice before giving up the CPU, a waste of CPU cycles. However, multiple CPU spin locks works reasonably well if the number of threads roughly equals the number of CPUs. The thinking goes as follows. Imagine thread A on CPU 1 and thread B on CPU 2, both contending for a lock. If thread A grabs a lock and then thread B tries to B with spin. However, presumably the critical section is short and thus soon the lock becomes available, discovered by thread B. Spinning to wait for a lock held on another processor doesn't waste many cycles in this case, thus can be effective. Another hardware primitive that some systems support is known as the compare and swap instruction or compare and exchange. The C pseudocode for this single instruction is found in figure 28.4. Compare and swap, pointer expected new. So original goes here. Check if original is expected. And then assign the new value and then return the original. The basic idea for compare and swap is to test whether the value at the address specified by pointer is equal to expected. If so, update the memory location pointed to by pointer with the new value. If not, do nothing. In either case, return the original value at that memory location. Thus allowing the code calling compare and swap to know whether it succeeded or not. How will it know whether it succeeded? You're calling the original value, right? So are you saying succeeded if like the pointer is now the new value? While compare and swap instruction with the compare and swap instruction, we can build a lock in a manner quite similar to that with test and set. For example, we could just replace the lock routine above with the following: 0 is expected, 1 is the new value. So what if an interrupt happens after this? Let's say original is equal to expected. This is uh, true. Well, the first time it will be true because the flag is 0. And then right after this, an interrupt happens and it goes to thread 2. And then thread 2 also, um, it sets the pointer to new, right? And then interrupt happens and goes back to thread 1. Thread 1 also sets the pointer to new. So both of them would have 1 as their flag. Unless this all of the entire function happens in one go and no interrupt happens in the entire function. That would make sense, but like how do you declare the entire function to be atomic? The rest of the code is the same as test and set example above. The code works quite similarly. It simply checks if the flag is 0 and if so, atomically swap in A1, thus acquiring the lock. Threads that try to acquire the lock while it is held will get stuck spinning until the lock is finally released. If you want to see how to make a C callable 86 version of compare and swap, the code sequence might be useful. Oh, there's only one. So global, all new. What is this ASM volatile? Finally, as you have sensed, compare and swap is a more powerful instruction than test and set. We will make use of this power in the future when we briefly delve into topics such as lock-free synchronization. However, if you build a simple spin lock with it, its behavior is identical to the spin lock we analyzed above. Load, linked, and store condition. It's going to take a long time. Some platforms provide a pair of instructions that work con- in concert to help build critical sections. On the MIPS architecture, for example, the load, linked, and store conditional instructions can be used in tandem to build locks and other concurrent structures. The C pseudocode for these instructions is as found in figure 28.5. What's happening in figure 28.5? Alpha PowerPC ARM provides similar instructions. The load linked operates much like a typical load instruction and simply fetches a value from memory and places it in the register. The key difference comes with a store conditional, which only succeeds if no intervening store to address has taken place. In the case of success, the store conditional returns 1 and updates the value at pointer to value. If it fails, the value at pointer is not updated and 0 is returned. So load linked, it just returns that pointer. What does this even do? If no update to pointer sends LL to this address. Pointer value return 1, else return 0. The load link operates much like a typical load instruction and simply fetches a value from memory and places it in the register. Key difference comes with store conditional, which only succeeds if no intervening store to the address has taken place. In the case of success, the store conditional returns 1 and updates the value to pointer to value. Okay. As a challenge to yourself, try thinking about how to build a lock using load linked and store conditional. I guess we can check if load linked is equal to our value. If load linked is equal to our value, then it means it was updated in the other thread. Then we shouldn't go here, then we should just return 0. I think that's how they would do it. The lock code is the only interesting piece. First, the thread spins, waiting for the flag to be set to 0. Solution is in figure 28.6. So while load length is equal to 1, spin, if store conditional is 1, then return. First, the thread spins, waiting for the flag to be set to 0. Once so, the thread tries to acquire the lock via the store conditional. If it succeeds, the thread has automatically changed the flag value to 1 and thus can proceed into critical suction. Note how failure of store conditional might arise. One thread calls lock and executes the load link, returning 0 as the lock is not held. Before it can attempt the store conditional, it is interrupted and another thread enters the lock code, also executing the load linked instruction and also getting a 0 and continuing. At this point, two threads have each executed the load linked and each are about to attempt the store conditional. The key feature of these instructions is that only one of these threads will succeed in updating the flag to 1. Okay, so let's say two threads, both of them enter the store condition. Both of them checked load linked. This was false. Now both of them somehow enter the store conditional. Thread 1 enters store conditional and and uh, and then it updated the value to 1 and then an interrupt happens. And then thread 2, for the thread 2, same thing. It updates the value to 1 and an interrupt happens. So for thread 1, this would be true, and then interrupt, and thread 2, this would also be true unless the entire function is atomic. The second thread attempts the store condition. The second thread to attempt the store conditional will fail because the other thread updated the value of flag between its load link and store conditional and thus have to try to acquire the lock again. In class a few years ago, undergraduate student David Capel suggested a more concise form of the above. For those of you who enjoy short-circuiting Boolean conditions, see if you can figure out why it is equivalent. It certainly is shorter. So while load length, while this is 1, so it can only be 1 or 0. While this is 1 and so sorry, while this is 1, why is it or? Okay, while this is 1, keep spinning, or while this is not 1, keep spinning. So we don't need the while loop over here. One final hardware primitive is the fetch and add instruction, which atomically increments a value while returning the old value at a particular address. The C pseudocode for the fetch and add instruction looks like this. Fetch and +1 and old. Less code is better code. Programmers tend to brag about how much code they wrote to do something. Doing so is fundamentally broken. What one should brag about rather is how little code one wrote to accomplish a given task. Short, concise code is always preferred. It is likely easier to understand and has fewer bugs. As Hugh Lohr said in discussing the construction of the pilot operating system, the same people had twice as much time. They could produce a as good of a system in half the code. We'll call this Lohr's law, and it is still worth remembering. So next time you're bragging about how much code you wrote to finish the assignment, think again. In this example, we will use fetch and add to build a more interesting ticket lock. As introduced by Miller, Rami, and Scott, the lock and unlock code is found in 28.7. So lock, ticket, turn. Lock ticket is 0, lock turn is 0. So my turn, fetch ticket. So what does this do? Pointer. So it returns the old value and increments the pointer. So ticket, it returns the old value. So my turn would be 0. While lock turn is not my turn. But my turn would be, so it returns 0, my turn would be 0. And then when thread 2, wait, so thread 1 won't experience this. Suppose thread 1 is in this function, now thread 2 is using this function again. And it gets the ticket of 1, but sorry, it gets the ticket of 1, so the turn is 1, but lock turn is still 1, right? It's still 0. Only when thread 1 unlocks it, it will turn to 1. Instead of a single value, this solution uses a ticket and turn variable in combination to build a lock. The basic operation is pretty simple. When a thread wishes to acquire a lock, it first does an automatic fetch and add on the ticket value. That value is now considered this thread's turn. The globally shared lock turn is then used to determine which thread's turn it is. When my turn is turn for a given thread, it is that thread's turn to enter the critical section. Unlock its accomplished Unlock is accomplished simply by incrementing the turn such that the next waiting thread can now enter the critical section. The one important difference with this solution versus our previous one is it ensures progress for all threads. Once a thread is assigned its ticket value, it will be scheduled at some point in the future. In our previous attempts, no such guarantee exists. A thread spinning on test and set could spin forever even as other threads acquire and release the lock. Wait, in test and set, let's go back up. Test and set. So are they saying if the other thread doesn't unlock, the first thread will keep spinning forever? A thread spinning on set and test could spin forever even if the other threads acquire and release the lock. How though? Test and set. So it sets the flag to 0. One thread sets the flag to 0. The other thread would know this is now not 0, right? Yeah, I didn't understand that part. One hardware-based locks. Our hardware-based locks are simple, only a few lines of code, and they work, which are two excellent properties of any system or code. However, in some cases, these solutions can be quite inefficient. Imagine you are running two threads on a single processor. Now imagine that one thread is in a critical section and thus has a lock held, and unfortunately gets interrupted. The second thread now tries to acquire the lock, but finds that it is held. Thus, it begins to spin and spin. Then it spins some more, and finally, a timer interrupt goes off. Thread 0 is run again, which releases the lock, and finally, thread 1 won't have to spin so much and will be able to acquire the lock. Thus, anytime thread gets caught spinning in a situation like this, it wastes an entire time slice doing nothing but checking a value that isn't going to change. The problem gets worse with n threads contending for a lock. N minus 1 time slices may be wasted in a similar manner. So, how to avoid spinning? Hardware support got us pretty far, working locks and even fairness in lock acquisition. However, we still have a problem. What to do when a context switch occurs in a critical section and threads start to spin endlessly waiting for the interrupted thread to be run again? Our first try is simple and friendly approach. When you are going to spin, instead give up the CPU to another thread. As AI Davis might say, just yield. Al Davis, figure 28.8 shows this approach. So initiate flag while test is set to 1, yield. But it is nothing over here, right? It is nothing during the spin, right? Like spin isn't an actual function, it's just stuck in a while loop. In this approach, we assume an operating system primitive yield, which call a thread can call what it wants to give up the CPU and let another thread run. A thread can be in one of three states: running, ready, or blocked. Yield is simply a system call that moves the caller from the running state to the ready state and thus promotes another thread to running. Thus, the yielding thread essentially reschedules itself. Think about the example with two threads on one CPU. In this case, our yield-based approach works quite well. If a thread happens to call lock and find a lock field, it will simply yield the CPU and thus the other thread will run and finish its critical section. In this simple case, the yielding approach works well. Now, let us consider the case where there are many threads, say 100, contending for a lock repeatedly. This case, if one thread acquires the lock and it is preempted before releasing it, the other 99 will each call lock, find the lock held, and yield the CPU. Assuming some kind of round-robin scheduler, each of the 99 will execute this run yield pattern before the thread holding the lock gets to run again. While better than a spinning approach, which would waste 99 time slices spinning, this approach is still costly. The cost of context switch can be substantial, and there is thus plenty of waste. While this approach does not address starvation, a thread may get caught in an endless yield loop while other threads repeatedly enter and exit the critical section. We clearly need an approach that addresses starvation directly. The real problem with some previous approaches is that they leave too much to chance. The scheduler determines which thread runs next. If the scheduler makes a bad choice, a thread that runs must either spin waiting for the lock or yield the CPU immediately. Either way, there is potential for waste and no prevention of starvation. Thus, we must explicitly exert some control over which thread next gets to acquire the lock after a current holder releases it. To do this, we will need a little more voice support, as well as a queue to keep track of which thread are waiting to acquire the lock. For simplicity, we will still use the support provided by Solaris in terms of two calls: park to put a calling thread to sleep, and unpark to wake a particular thread as designated by thread ID. These two routines can be used uh, in tandem to build a lock that puts a caller to sleep if it tries to acquire a held lock and wakes it when the lock is free. Let's look at the code in 28.9 to understand one possible use of such primitives. So, structure, lock, flag, guard, queue. Flag is 0, guard is 0, queue. Okay, M, Q. So void, lock, while less than set the M guard. Acquire guard lock by spinning. Flag is 0, turn the flag to 1, turn the guard to 0. Else add to Q. Get ID, guard is 0 and park. Okay, this one is quite confusing. We do a couple of interesting things in this example. First, we combine the old test and set idea with an explicit queue of lock waiters to make a more efficient lock. Second, we use a queue to help control who gets the lock next and thus avoid starvation. Might notice how the card is used. Basically, as a spin lock around the flag in queue manipulations, the lock is using. This approach thus doesn't avoid spin waiting entirely. A thread might get interrupted while acquiring or releasing the lock and thus cause other threads to spin wait for this one to run. However, the time spent spinning is quite limited. Just a few instructions inside the lock and unlock code instead of the user-defined critical section, and thus this approach may be reasonable. Flag. Acquire guard lock by spinning. Okay, I'm a little confused on this one. You might also observe that in lock, when a thread cannot acquire the lock, we are careful to add ourselves to a queue calling the getID function to get a thread ID of the current thread. Set the card to 0 and yield the CPU. Add queue, set the card to 0 and bark. You might also observe that in a lock, when a thread cannot acquire the lock, we must carefully add ourselves to the queue. Set the card to 0 and yield the CPU. Question for the reader. What would happen if the release of the card lock came after the bark and not before? Hint something bad. You might further detect that the flag does not get set back to 0 when another thread gets woken up. Why is this? Well, it is not an error but rather a necessity. When a thread is woken up, it will be as if it is returning from park. However, it does not hold the card at that point in the code and thus cannot even try to set the flag to 1. Thus, we just pass the lock directly from the thread, releasing the lock to the next thread, acquiring it. Flag is not set to 0 in between. Finally, you might notice the perceived race condition in the solution. Just before the call to park. With just the wrong timing, a thread will be about park, assuming that it should sleep until the lock is no longer held. A switch at that time to another thread could lead to trouble. For example, if that thread then released the lock, subsequent park by the first thread would then sleep forever. A problem sometimes called wake up waiting race. Solaris solves this problem by adding a third system called set park. By calling this routine, a thread can indicate it is about to park. If it then happens to be interrupted and another thread calls on park before park is actually called, the subsequent park returns immediately instead of sleeping. The code modification inside a block is quite small. A different solution could pass the card into the kernel. In that case, the kernel could take precautions to atomically release the lock and dequeue the running thread. We have thus seen one type of support that an OS can provide in order to build a more efficient lock in the thread library. Other OSs provide similar support. The details vary. For example, Linux provides a Vutex, which is similar to Solaris interface, but provides some more in-kernel functionality. Specifically, each Vutex has associated with it a specific physical memory location as well as a per Vutex in kernel queue. Callers can use Vutex calls to sleep and wake as need be. Specifically, two calls are available. The call to Vutex wait puts the calling thread to sleep, assuming the value at the address is equal to expected. If it is not equal, the call returns immediately. The call to routine wakes one thread that is waiting on the queue. The usage of these calls in a Linux mutex is shown in figure 28.10. Void mutex lock. Atomic bit test set. Atomic increment. Bit 31 was clear, we got mutex. Then return. While 1, if atomic bit test set is 0, atomic decrement. And then return. Have to wait first to make sure mutex value we are monitoring is negative. Mutex wait. Mutex v. Okay, these last few examples are slightly confusing for me. This code snippet from low-level lock.h in the NPTEL library is interesting for a few reasons. First, it uses a single integer to track both whether a lock is held or not and the number of waiters on the lock. If the lock is negative, it is held. Second, the code snippet shows how to optimize for the common case. Specifically, when there is no contention for the lock, with the only thread acquiring and releasing a lock, very little work is done. See if you can puzzle through the rest of this real world lock to understand how it works. Do it and become a master Linux locking, or at least somebody who listens when a book tells you to do something. One final note: the the Linux approach has the flavor of an old approach that has been used on and off for years, going at least as far back to dam locks in the early 1960s. Is now referred to as a two-phase lock. A two-phase lock really realizes that spinning can be useful, particularly if the lock is about to be released. So, in the first phase, the lock spins for a while, hoping that it can acquire the lock. However, if the lock is not acquired during the first spin phase, second phase is entered, where the caller is put to sleep and only woken up when the lock becomes free later. The Linux lock above is a form of such a lock, but it only spins once. A generalization of this could spin in a loop for a fixed amount of time before using Futex support to sleep. Two-phase locks are yet another instance of a hybrid approach, where combining two good ideas may yield a better one. Of course, whether it does depends strongly on many things, including the hardware environment, number of threads, and other workload details. The above approach shows how real locks are built these days, some hardware support, plus some operating system support. Of course, the details differ and the exact code to perform such locking is usually highly tuned. Check out the Solaris and Linux code bases if you want to see more detail. Okay, then. I will end the stream here then. And yeah, I'll see you guys in the next chapter. Bye.